Section 1 Introduction. Training neural networks requires a significant amount of computational resources. One way to improve this process is by utilizing low-precision arithmetic, also known as fully quantized training, FQT. This technique enhances the computational and memory efficiency by replacing high-cost floating-point operations with less expensive, low-precision ones. Researchers use FQT methods to decrease the precision of the training numerals, with the goal of not losing too much accuracy or speed during the training process. In the past, the required numerical precision was reduced from 16-bit floating point, FP16, to 8-bit floating point, FP8, then to a combination of 32-bit and 8-bit integers, INT32 plus INT8, and further down to a combination of 8-bit and 5-bit integers, INT8 plus INT5. For instance, the FP8 training method was employed in NVIDIA's H100 GPU, which resulted in notable speed boosts when training large-scale transformer models. More recently, the precision of these training numerals has been reduced even further, down to 4 bits. For example, Sun and others successfully trained several modern networks using 4-bit integer activation, weights and 4-bit floating point gradients. Camille and others proposed a unique 4-bit logarithmic numerical format to enhance accuracy. However, these 4-bit methods can't be directly used to accelerate the process as they require unique numerical formats that are not supported by the current generation of hardware. There are some significant optimization challenges when it comes to training neural networks at an ultra-low 4-bit level. For starters, the forward propagation process employs non-differentiable quantizers which create a rugged loss landscape, making it easy for gradient-based optimizers to get trapped in local optima. Furthermore, gradients are calculated approximately in low precision, causing the training process to be slower and sometimes unstable or divergent. In our work, we present an innovative 4-bit integer, INT4, training algorithm for a type of widely used neural networks, known as transformers. All the expensive linear operations required for training transformers can be represented as matrix multiplications. This format allows us to design more adaptable quantizers that can more accurately approximate 32-bit floating-point matrix multiplications. They achieve this by leveraging the specific structures of activations, weights, and gradients in transformers and using techniques from the field of randomized numerical linear algebra, RAND-NLA. For forward propagation, we discovered that outliers in the activation cause a significant decrease in accuracy. To counter this, we propose a Hadamard quantizer, which quantizes a transformed version of the activation matrix. This transformation spreads the information contained in outliers across nearby entries in the matrix, reducing the numerical range of these outliers. In the case of backpropagation, we use the structural sparsity of activation gradients. We found that the gradients of a few tokens are quite large, while the majority of them are very small, even smaller than the quantization residuals of larger gradients. Instead of computing these small gradients, it's more efficient to allocate computational resources to calculate the residuals of the larger gradients. To leverage this sparsity, we propose bit splitting, which splits the gradient of each token into higher and lower 4 bits. We then select the most informative gradients using leveraged score sampling, an important sampling method used in RAND-NLA. By combining the quantization techniques used for forward and backward propagation, we introduce an algorithm that uses 4-bit integer matrix multiplications for all linear operations in transformers. We've tested our algorithm on a wide range of tasks, including natural language understanding, question answering, machine translation, and image classification, and it has proven to be as accurate or more accurate than existing 4-bit training methods. Additionally, our algorithm can be implemented on current generation hardware like GPUs, as it doesn't need unique numerical formats like 4-bit floating point or logarithmic formats. Our prototype, which combines quantization and 4-bit integer matrix multiplication, performs up to 2.2 times faster than the 16-bit floating point matrix multiplication baseline, accelerating training by up to 35.1%. Section Summary. The paper discusses the challenges of training neural networks with low-precision arithmetic, specifically at the 4-bit level. The authors propose a novel int4 training algorithm for transformers that utilizes flexible quantizers and exploits the structural sparsity of activation gradients. The algorithm achieves competitive or superior accuracy compared to existing works on 4-bit training and is compatible with contemporary hardware like GPUs. Section 2 Related Work. We'll begin by discussing related work in this field. The concept of fully quantized training, or FQT, comes first. This method speeds up the training process by turning the activations, weights, and gradients into low-precision formats. Consequently, both linear and nonlinear calculations during training can be executed using less complex math. The focus of researchers working on FQT is creating new numerical formats and quantization techniques that closely emulate full precision tensors, which can be thought of as a higher dimensional analog to vectors and matrices. The latest frontier in this domain is 4-bit FQT. However, FQT is not without its challenges. The wide numerical range of the gradient and the complexity of optimizing a quantized network from scratch present significant obstacles. As a result of these difficulties, current 4-bit FQT algorithms still exhibit a slight decrease in accuracy, between 1 and 2.5%, across a range of tasks. Furthermore, these algorithms are incompatible with modern hardware. Beyond FQT, there are other strategies for efficient training as well. For example, the mixture of experts approach enhances the model's capacity without inflating the training budget. The method called structural dropout leverages computationally efficient ways to add regularization to the model, which can help prevent overfitting. Efficient attention is another approach that diminishes the time complexity for computing attention, which is a mechanism that allows models to focus on relevant features in the data. Lastly, distributed training systems cut down on training time by harnessing additional computational resources. Our efforts to decrease numerical precision can be seen as complementary to these methods. We're operating in a different, but related, sphere. Section Summary. Fully quantized training, FQT, methods accelerate training by quantizing activations, weights, and gradients to low precision, but existing 4-bit FQT algorithms still have accuracy drops and cannot support contemporary hardware. Other efficient training methods include mixture of experts, structural dropout, efficient attention, and distributed training systems, which are orthogonal to our work on reducing numerical precision. Section 3. Forward propagation. Let's dive into the concept of forward propagation in the training of neural networks. This is essentially a repetitive process of optimizing via stochastic gradients, achieved by alternating between forward and backward propagation. In our study, we utilize 4-bit integer arithmetic, abbreviated as int4, to expedite these propagation processes. Now, let's delve a bit deeper into the specific details of our forward propagation method. You can think of forward propagation as a mix of linear and nonlinear operations. Examples of nonlinear operations include the Gaussian error linear unit, GLU, normalization, softmax, and others. What we've done in our method is to speed up all linear operations using int4 arithmetic, while keeping the less computationally heavy nonlinear operations in a 16-bit floating point, or FP16, format. What do we mean by linear operations? Simply put, they're operations that can be represented in the form of matrix multiplication. So, for simplicity's sake, let's focus on how we've accelerated a basic matrix multiplication throughout our research. Picture it this way. We have a matrix multiplication equation Z equals XW caret T, where Z is a matrix with dimensions nxm, X is a matrix with dimensions nxk, and W is a matrix with dimensions mxk. This type of matrix multiplication is most commonly found in fully connected layers of a neural network. Imagine a transformer with an input shape defined by batch size S, sequence length T, and dimensionality D. The fully connected layer would then be represented by the aforementioned equation, where X signifies the activation for north equals street tokens, and W is the weight matrix. In the case of attention layers, we might need to conduct batch matrix multiplications, or BMMs. The techniques we propose can be applied to these BMMs as well. For further details on how these BMMs are handled, please refer to the appendix. Section Summary. The training of neural networks involves iterative optimization with stochastic gradients computed by forward and back propagation. The forward propagation is composed of linear and nonlinear operators, and in this paper, the linear operators are accelerated with 4-bit integer arithmetic while the nonlinear operators are left in 16-bit floating point format. The acceleration is demonstrated through a simple matrix multiplication, which can be applied to fully connected layers in transformers. Section 3.1. Learned step-size quantization. To speed up the training process, we need to carry out forward propagation using integer arithmetic. We use a method called learned step-size quantization, LSQ, to accomplish this. LSQ is a type of static quantization approach, meaning that the scale of quantization doesn't vary based on the input. This makes it more cost-effective than dynamic quantization methods, which must calculate the scale of quantization for each iteration. Let's simplify this process. Given a floating point matrix, let's call it X. LSQ changes this matrix into an integer form. This process involves a few steps. 1. First, we divide every element in the matrix X by a learnable scalar parameter, symbolized as Sx. This operation is performed element-wise. 2. Then, we constrain the resulting values to a range between Qn and Qp. This is done using a function called clamp. 3. Following this, we apply a rounding operation to ensure we get whole numbers. 4. The final integer matrix can have values from Qn to Qp, with all the whole numbers in between. Since our goal is to work with 4-bit integers, int4, in matrix multiplication, we set both Qn and Qp to 7. Now, if we need to turn the integer matrix back to a floating point form, we just multiply it by Sx. This means the original floating point matrix x is approximately equal to Sx times the integer matrix. Using LSQ, we can approximate the calculation of a new matrix, y, which is a product of the matrix x and the transpose of a weight matrix, w. Here, the matrix multiplication between the integer versions of x and w can be performed efficiently on hardware. The resulting matrix, y, is then scaled by multiplying Sx with a similar scalar parameter for the weight matrix, Sw. This way, we preserve the original scale of the values. Section summary. To speed up training, we use the Learned Step Size Quantizer, LSQ, which quantizes a floating point matrix x to an integer matrix with values from -7, -6, 7. LSQ is a static quantization method that uses a learnable scalar parameter s_x to compute the quantization scale, making it cheaper than dynamic quantization methods. The integer matrix can be dequantized back to floating point, allowing for efficient implementation of the int4 matrix multiplication. Section. Remark. We want to highlight a key point here. Quantization-aware training, or QAT, is a technique used to speed up inference in neural networks. This process incorporates quantizers into the network's forward propagation graph during training. The outcome is a trained network that is much more efficient when performing inference. Notably, QAT can shrink the precision of activations and weights to an exceptionally low level, often down to just 1 or 2 bits. At first glance, you might think that applying a quantizer for QAT to full quantization training, or FQT, would yield similarly low activation and weight bit widths. But this assumption oversimplifies the complexity of the situation. In fact, using only forward propagation quantization for FQT presents far greater challenges than it does for QAT. Here's why. 1. First, QAT necessitates a fully precision model that has converged to be used either for initialization or as a source for knowledge distillation. 2. Second, QAT can use more resource-intensive multi-stage training pipelines without having to worry about how quickly the model converges. In contrast, FQT algorithms must converge at the same rate as full precision training algorithms to be deemed useful. 3. Third, QAT has the flexibility to approximate the discrete quantizer with continuous functions during the training process. Unfortunately, this approximation can't be achieved using integer arithmetic, which is a limitation for FQT. Because of these hurdles, finding a way to perform FQT with 4-bit activations and weights remains an unresolved issue in the field. Section summary. Quantization-aware training, QAT, is a technique that trains networks with quantizers to compress activation weights to low precision for efficient inference. However, applying a quantizer for QAT to FQT is more challenging because FQT requires a converged full precision model as initialization, must converge as fast as full precision training algorithms, and cannot approximate the discrete quantizer with continuous functions during training. Therefore, it is still an open problem to do FQT with 4-bit activations, weights. Section 3.2 Activation Outliers. Section 3.2 Addressing Outliers in Activation. If we directly apply the least squares quantization, LSQ, method for fixed-point quantization training, FQT, using 4-bit activation and weights, the model accuracy tends to decline. This is primarily due to outliers in activation values. As depicted in the given figure, some activation entries significantly exceed others in magnitude. The step size, denoted as s_x, presents a balancing act between the granularity of quantization and the numerical range that can be represented. A large step size allows for effective representation of outlier values, but unfortunately, this comes at the cost of a very rough representation for most other entries. Conversely, with a smaller step size, we are forced to cut off the entries that fall outside the range, represented by Q_n, s_x, Q_p, s_x. Unfortunately, transformers tend to keep important information within these outlier values, and discarding them can lead to a significant loss in accuracy. This issue becomes particularly noticeable when the task is to fine-tune a pre-trained model for new downstream tasks. Pre-trained models, as compared to models initialized randomly, contain a higher number of outliers. There are existing approaches to handle activation outliers in post-training quantization, PTQ. For instance, outlier suppression found that layer normalization tends to magnify outliers and proposed two solutions: gamma migration and token-wise clipping. These methods proved successful in achieving 6-bit BERT PTQ with minimal degradation. Another method, smooth quant, shifts the challenge of handling activation outliers to the weights, allowing for 8-bit PTQ in larger language models like OPT175B. Furthermore, outlier channel splitting duplicates the channels containing outliers, thereby keeping the increase in the network size minimal. However, these techniques are primarily designed for PTQ or quantization-aware training, QAT, and have not been seen to effectively deal with 4-bit training. Section Summary. When applying LSQ for FQT with 4-bit activation, weights, accuracy degradation occurs due to activation outliers. These outliers pose a trade-off between quantization granularity and representable numerical range, and truncating them harms accuracy. Existing methods for handling activation outliers mainly focus on post-training quantization or quantization-aware training, and are not effective for ultra-low 4-bit training. Section 3.3 Hadamard Quantization. In this section, we propose a method called Hadamard quantization. This method targets the outlier problem, which typically shows up as irregularly large values in the activation matrices. These outliers often concentrate in a few dimensions, meaning only a few columns of the matrix X have significantly larger values than the others. Our proposed solution applies the Hadamard transform, a specific type of linear transformation, to the matrices. This transforms the matrix into another space where these outliers are spread or amortized across multiple entries. To understand the Hadamard transform, let's look at an example. Imagine a matrix H_k that has a size of 2 raised to the power of k by 2 raised to the power of k. Here, H_0 is a 1 by 1 matrix with a single element, 1. The value of H_k can be created by placing the previous Hadamard matrix, H_k1, in 4 quadrants, with the last quadrant being negated, and each value being divided by the square root of 2. These Hadamard matrices possess a couple of important properties. Firstly, they are orthogonal and symmetric. This means that the matrix is identical to its own transpose and its own inverse. Secondly, when any coordinate row vector, a vector with one dimension as 1 and all others as 0, multiplies with the Hadamard matrix, it results in a vector of equal dimensions, where all entries are 1. When the original vector is dominated by a single outlier, the Hadamard transformation effectively turns it into a quantization-friendly vector of 1s, reducing the impact of the outlier. To implement this in practice, we employ a block diagonal transformation matrix H with dimensions d by d here. D is a multiple of 2 to the power of k. We then apply this transform to our original matrix X, effectively turning it into a new matrix that is more conducive to quantization. Once this transformation has been made, we can use it to smoothen out the outliers in the activation matrix. We do the same for the weight matrix W. After these transformations, we can multiply the two matrices together to achieve the final result. This process can be summarized into 4 steps. 1. Compute XH and HW_T and 16-bit floating point. 2. Quantize the resultant matrices to INT4. 3. Multiply the two int4 matrices. 4. Dequantize the resultant int32 matrix back to 16-bit floating point by multiplying two scaling factors. As for computational complexity, the first step takes O(2)k*n*, d plus c. 16-bit floating point operations, the second and fourth steps take O(n*, d plus c. 16-bit floating point operations, and the third step takes O(n*, d*, c, int4 operations. There is a trade-off between the ability to suppress outliers and computational complexity. A larger value of k allows for more distributed amortization of the outlier, but at the expense of increased computational complexity. Therefore, we suggest an adaptive approach to choose the value of k for each activation depending on the scale of outliers. Typically, we find that k equals 5 is a reasonable choice, with dimensions c and d ranging from 768 to 4096. Section Summary. The Hadamard quantizer, HQ, is proposed to solve the outlier problem by quantizing matrices in another linear space with fewer outliers. The Hadamard transform is used to amortize the outliers into other entries, NA. Block diagonal transformation matrix is used to suppress outliers. The HQM procedure involves computing, quantizing, multiplying, and dequantizing matrices, and the number k shows a trade-off between the ability to suppress outliers and computation complexity. Section 4. Backpropagation. In Section 4, we discuss ways to speed up the backpropagation process of the linear layer by using int4 operations. The linear operator, represented by HQM in equation x, not given, has 4 input elements: the activation, represented by x, weight, represented by w, and step sizes represented by s_x and s_w. If we consider the output gradient in relation to a particular loss function, L, we need to determine the gradient for all 4 inputs. This section focuses on the computation of activation, weight gradients, and we'll be discussing the step size gradients later in the appendix. In our explanations, we'll keep things simple by leaving out the loss function, L, and use the term gradient for the output. Using the straight-through estimator and chain rule, we have our gradient for weight, W, and activation, X. Here, we are using some notations. X hat and W hat are representations of our activation and weight where we round off to the nearest integer after multiplying by the step size and performing Hadamard operation. I_X and I_W are indicators that are checking whether the normalized activations and weights fall between Q_N and Q_P. Now, to calculate these gradients, we need 3 types of matrix multiplications. 1. The first type involves multiplying a binary matrix, I_X or I_W, with another matrix, int4 or int32, element-wise. This operation is not time-consuming. 2. The second type involves the multiplication of an int32 matrix with an fp16 block-wise Hadamard matrix, represented by s_W multiplied by the transpose of H. This operation, too, isn't time-consuming and was discussed in a previous section. 3. The third type is multiplying the fp16 gradient with an int4 matrix, represented by x hat or w hat. We'll speed this process up by changing the gradient into int4. For the remainder of this section, we will delve deeper into the methods of quantizing or converting the third type of matrix multiplications. We're going to dynamically quantize the gradient for each multiplication, while x hat and w hat were already calculated in the forward propagation stage, which we discussed in a previous section. Now, let's discuss the gradient structure. Section Summary. The section discusses the acceleration of backpropagation of the linear layer with int4 operations. The computation of activation, weight gradients is discussed, while the discussion of step size gradients is left to the appendix. 3 types of matrix multiplications are required for computing the gradients, and the section focuses on quantization methods to compute the type 3 inches matrix multiplications. Section 4.1 Structural sparsity of gradients. We've observed that the gradient matrix of the neural network, which we'll refer to as Y gradient, exhibits high levels of sparsity during the training process. Interestingly, this sparsity isn't random but follows a specific structure. A few rows, which represent tokens, of the Y gradient contain large values, while most others are nearly equivalent to zero-filled vectors. We've captured this trend visually through a histogram, which displays the per row norms of the Y gradient. The observed structured sparsity seems to arise from the extensive overparameterization seen in modern neural networks. Over the course of the training process, the network largely operates in an overparameterized state, being able to efficiently fit most of the training data, except for a handful of challenging examples. As a result, the gradient related to activation ends up being close to zero for those data points that are well fitted. For pre-training tasks, we noticed that this kind of structured sparsity starts showing up quite early, just after a few epochs. When it comes to fine-tuning tasks, the gradient remains sparse throughout the entire training process. Having acknowledged the sparsity of gradients, we want to discuss how to develop gradient quantizers that accurately compute the matrix multiplications, MMs, during backpropagation, by taking advantage of this structured sparsity. The overarching idea is that many rows of the gradient are so minuscule that they hardly affect the parameter gradient, yet they consume significant computational resources. On the contrary, the large rows cannot be accurately represented using a 4-bit integer, int4. We can make our computations more efficient by excluding some small rows and using the saved computation power to more accurately represent large rows. One technique we propose is bit splitting, BS, which separates a full precision matrix into higher and lower 4-bit components. In other words, we can approximate the Y gradient as the sum of 2 parts, one part scaled by an upward floating point scalar and representing the higher 4 bits, and the other part scaled by a downward floating point scalar and representing the lower 4 bits. Bit splitting can be achieved by first quantizing the Y gradient to int4 and then quantizing the residual to int4. Essentially, Bit splitting provides an 8-bit integer, int8, representation of a matrix, where the upper and lower 4-bit parts represent the higher and lower bits of the int8 representation, respectively. Next, we're going to discuss how we calculate the weight and activation gradient. Section summary. The gradient matrix nabla_y tends to be very sparse during the training process, with few rows having large entries while most other rows are close to an all-zero vector. This structural sparsity arises from the heavy overparameterization of modern neural networks. To accurately compute the MMs during backpropagation, the authors propose bit splitting, BS, which splits a full precision matrix as higher and lower 4 bits, dropping small rows and using the saved computation to represent large rows more accurately. BS can be viewed as an int8 representation of a matrix, where nabla_y, up arrow, and nabla_y, down arrow, are the higher and lower 4 bits of the int8 representation. Section. Weight gradient. As previously mentioned, the gradient of a weight, or weight gradient, involves matrix multiplication denoted as the transpose of y gradient matrix times the x hat matrix. Here, the y gradient matrix belongs to an n by c real number space and x hat is an n by d int4 matrix. According to our equation, the multiplication of the transpose of y gradient matrix and x hat matrix can be approximated as the product of the up and down scaled parts of y gradient with x hat matrix. This generates a new version of the y gradient and x hat matrices, both doubled in size. This equation is essentially the product of an 8-bit y gradient transpose, int8, and a 4-bit weight, int4, which can be computed by two separate 4-bit matrix multiplications. This method tends to be accurate as the y gradient is represented with 8 bits. However, compared to a straightforward 4-bit quantization of the y gradient, this method doubles the number of 4-bit operations for matrix multiplication. We propose using leverage score sampling, LSS, to reduce the operations of the equation by half, bringing it to the same quantity as the straightforward matrix multiplication. We also note that our equation can be rewritten as the sum of two n rank 1 matrices. Due to the sparse nature of the y gradient, the resulting matrices vary in magnitude, and smaller matrices can be discarded with negligible impact on the result. LSS assigns each matrix a probability that ranges between 0 and 1 and ensures that the sum of all probabilities equals n. We define random masks and a mask matrix to get an unbiased approximation of the equation. As a result, on average, there are only n non-zero masks. Therefore, LSS can reduce the computational cost of matrix multiplication by half. To ensure the accuracy of LSS, we aim to minimize its variance. The leverage score, a product of the norms of the corresponding rows from the y gradient and x matrices, is used in this context. It can be computed with low time complexity. We find that when the probability is proportional to the leverage score, the variance reaches its minimum. Intuitively, LSS can approximate matrix multiplication well with significantly lower computational cost when the leverage scores are diverse, which is often the case as shown in our experiments. Using this approach, we can implement the equation as two separate 4-bit matrix multiplications with sampled rows, columns. In summary, we propose the following method to compute the weight gradient. 1. Quantize the y gradient to get its upper and lower parts in 4-bit integer form. 2. Calculate the leverage score in 16-bit floating point precision. 3. Sample the masks. 4. Sample rows of the y gradient and x hat given the masks. 5. Compute 4-bit integer matrix multiplications. 6. Dequantize and sum up the resultant 32-bit integer matrices to obtain the 16-bit floating point result. Since the mask matrix is expected to have only n non-zero elements, the two matrix multiplications in step 5 take roughly the same amount of 4-bit multiply accumulate operations as the straightforward matrix multiplication. The overhead of all the other steps is proportional to the size of the matrices. Section summary. The weight gradient involves matrix multiplication of nabla_y, top, hat, x, which can be implemented accurately with two int4 MMs but doubles the amount of int4 operations. To reduce the cost of m by half, leverage score sampling, LSS, is proposed, which assigns each nabla_w_i a probability p_i in 0, 1, I equals 1, c dots, 2n, that satisfies sum_i equals 1, 2n, p_i equals n. LSS can approximate the MEQ. Well, with significantly lower computational cost when the leverage scores, c_i, are diverse. Section. Activation gradient. Let's talk about the activation gradient. As with the prior discussions, we can describe the change in input as a mathematical expression which involves two main components, represented here by symbols S and nabla. These two components correspond to the up and down direction, respectively. Together, they form a new expression that we can represent with the symbol W. This expression can be broken down into two parts that combine to form the whole. Now, it's important to note that we've defined a new symbol, nabla_y, to represent the two directional components in a two-dimensional space. Additionally, we've also defined another symbol, I, which is essentially a matrix made up of n by two n integers, with n being an identity matrix. While the original product can be created using two int4 MMs, here represented by nabla_y, in up and down directions and W, it's important to focus on the term I_nabla_y in the given equation. This term is particularly important because it leverages score sampling on this matrix multiplication. Now, to dive a little deeper into this, we can write the matrix multiplication as a sum of two n smaller multiplications. We define nabla_y, an associate probability and Bernoulli mask with the I multiplication. The leverage score for activation gradient is defined by C_I, and the variance is at its minimum when the probability is proportional to C_I. Finally, on the implementation side, once we know the mask, we can break down the matrix multiplication equation into two int4 MMs. The breaking down or decomposition is done in a way such that we retain the core of the equation while also taking into consideration the up and down direction components. This decomposition maintains the balance and ensures the right mix of all components. For more intricate details about the algorithm, refer to the appendix. Section summary. The activation gradient can be expressed as a sum of two smaller multiplications, and leverage score sampling is used on this matrix. The probability of each multiplication is associated with a Bernoulli mask, and the variance is minimized when the probability is proportional to the leverage score. The M can be decomposed into two int4 MMs once the mask is known. Section 5 Experiments. We've put our int4 training algorithm to the test across a diverse range of tasks, including fine-tuning language models, machine translation, and image classification. We developed our HQM and LSSM algorithms using CUDA and Cutlass II. You can find the specifics of this implementation in the appendix of the paper. Instead of using standard floating-point linear operators, we opted to use our int4 implementation. The only exceptions were in the embedding layers, where we used LSQ, and in the last classifier layer, which we kept at full precision. All tested models use the standard architectures, optimizers, schedulers, and hyperparameters. Now, let's discuss the accuracy of the final models. We've compared these across different tasks and summarized the results in a table. The methods compared include full precision training, FP, INT8 training, INT8, FP4 training, which we've referred to as ultra-low, 4-bit logarithm quantization with LSQ for activations and weights, LSQ plus LUQ, and finally, our algorithm that employs HQ for forward and LSS for backpropagation, HQ plus LSS. Unfortunately, there's no public implementation available for ultra-low, so we've relied on the original paper for its performance on the machine translation task. For all tasks, except large-scale machine translation and large vision transformers, we've run each task 3 times and reported the standard deviation in the tables. These repetitions help ensure the reliability of our results. Importantly, we didn't incorporate any form of knowledge distillation or data augmentation in our experiments. Section summary. The int4 training algorithm was evaluated on various tasks such as language model fine-tuning, machine translation, and image classification. The HQM and LSSM algorithms were implemented using CUDA and Cutlass II, and the accuracy of the converged model was compared to other methods such as full precision training, INT8 training, and LSQ plus LUQ. The results showed that the proposed HQ plus LSS algorithm achieved competitive accuracy with other methods while using significantly less memory and computation. Section. Language model fine-tuning. We've taken the two popular pre-trained models, BERT base uncased and BERT large uncased, and put our method to the test on various datasets like GLUE DevSet, SQUAD, SQUAD2, Adversarial QA, CONLL2003, and SWAG. We're sharing the average results of these two BERT models specifically on the GLUE dataset, with more comprehensive findings available in the appendix. When compared to another approach known as LSQ plus LUQ, our method significantly outperforms it, with an average improvement of 5.5% in accuracy for the BERT base model and a whopping average improvement of more than 25% for the BERT large model. We've also conducted similar tests on other datasets including SQUAD, SQUAD 2.0, Adversarial QA, CONLL 2003, and SWAG. The trend continued with our method consistently exceeding the performance of LSQ plus LUQ on every task. We observed improvements of 1.8% and 3.6% in accuracy on SQUAD and SQUAD 2.0, respectively. Even on more challenging datasets like Adversarial QA, we recorded a rise of 6.8% in the F1 score, a measure of model's accuracy. Moreover, our method outperformed LSQ plus LUQ by 6.7% on SWAG and by 4.2% on CONLL 2003 in terms of accuracy. Beyond language model fine-tuning, we've also experimented with our method in the realm of machine translation. We pre-trained a transformer base model on the WMT14 English-German (ND) dataset. Please note, we replicated this experiment following Fairsick's recipe 3, which provides the Sacre Bleu score, a standardized score for machine translation. While ultra-low and LUQ reported a more optimistic original blue score, we found our method, referred to as HQ plus LSS, had about 1.0% degradation in the blue score. This is a smaller reduction than the 2.1% experienced by ultra-low, but a bit more than the 0.3% reported by LUQ. Regardless, the performance of HQ plus LSS is comparable to existing methods for this pre-training task, and importantly, it is compatible with current hardware. Section Summary. The authors fine-tuned BERT base uncased and BERT large uncased models and evaluated their performance on various datasets, achieving better results than LSQ plus LUQ on all tasks. They also applied their method to pre-training a transformer base model for machine translation, achieving comparable results to existing methods with better hardware support. Full results are listed in the appendix. Section. Image classification. In our research, we utilize pre-existing vision transformer, VIT, models that have been previously trained on ImageNet 21K. We then fine-tune these models on the CIFAR10, CIFAR100, and ImageNet 1K datasets. Our experiment involves using different variations of the VIT model, such as VIT B32 and VIT L32 for CIFAR datasets and VIT B32, VIT L32, and VIT L16 for ImageNet 1K. Upon fine-tuning on CIFAR10, we noticed an accuracy decrease of less than 0.5%. When comparing this to the LSQ plus LUQ technique, our method showed less degradation. In particular, LSQ plus LUQ demonstrated a decrease of 1% accuracy for VIT B32 and 0.6% for VIT L32. The same pattern is observed in CIFAR100 and ImageNet 1K tests. For instance, for CIFAR100, INT8, which is known for its complexity, already has around a 1% drop in accuracy. However, our method improved the accuracy by 1.1% for VIT B32 and 0.2% for VIT L32 compared to LSQ plus LUQ. For ImageNet 1K, we observed an accuracy increase of 2% for VIT B32, 2.6% for VIT L32, and 0.2% for VIT L32 compared to LSQ plus LUQ. We also explored the efficacy of our algorithm in pre-training a DAE-T small model on ImageNet 1K. We found that our method, HQ plus LSS, can converge to a similar accuracy level compared to LSQ plus LUQ, while being more friendly to the hardware. Additionally, we conducted ablation studies to examine the individual effectiveness of our forward and backward methods on the challenging COLA dataset. To test the different quantizers for forward propagation, we left the backpropagation in fluorine hexadecaphosphide. We initially validated the idea that outliers are the primary source of accuracy degradation in quantized forward propagation. To do this, we examined an outlier method that keeps the 1% largest activation entries in fluorine monophosphide. The solid performance of the outlier method confirmed our hypothesis that outliers pose the most significant challenge for the transformer's forward quantization. Although the outlier method is not friendly to hardware, it serves as an upper limit for methods to manage outliers. We found that our HQ method surpasses LSQ by better managing the outliers, achieving results on par with the outlier method. Further, we explored whether more granular quantizers could be used to quantify outliers. We tested per token and per channel quantization and also existing methods like SmoothQuant for INT4FQT. We found that without HQ, none of these techniques achieved good accuracy under 4-bit quantization. However, the result of HQ is not strongly influenced when more granular quantization methods are applied. For backpropagation, we compared a simple minimax quantizer, LUQ, and our LSS, leaving a forward propagation in fluorine hexadecaphosphide. The Minimax quantizer divides the numerical range from the smallest to the largest into equal-sized quantization bins. We found that when the bit width is greater than 2, our LSS method delivers comparable, and occasionally better results than LUQ. Moreover, LSS is more compatible with hardware as it only requires int4 arithmetic. Section Summary. The paper discusses the use of VIT checkpoints pre-trained on ImageNet 21K, fine-tuned on CIFAR10, CIFAR100, and ImageNet 1K. The authors compare their HQ plus LSS algorithm to LSQ plus LUQ and find that HQ plus LSS achieves better accuracy while being more hardware-friendly. They also conduct an ablation study to show the effectiveness of their forward and backward methods independently on the COLA dataset. Section 5.3 Computational and Memory Efficiency. In Section 5.3, we showcase how our approach can speed up neural network training by testing out a basic version of our method. This implementation is provided in detail in the appendix. It's crucial to note, however, that our implementation isn't fully optimized. For instance, our approach's backward computation requires an int4 matrix multiplication in the form of y equals 2a times b. However, the software library we're using, known as Cutlass, only supports y equals to a times the transpose of b, so we need to transpose b explicitly, which adds an extra step. Plus, we've not yet combined the linear operators with nonlinear operations and normalization, which can further improve performance. Because of these reasons, the results we present here don't fully showcase the capability of int4 training algorithms. Optimizing our implementation completely would require a lot of additional work, and that falls outside the scope of our current paper. We also provide a speed comparison between our proposed method and a standard implementation. Our method includes components like HQMM, HQ, LSS for calculating the weight gradient, LSS weight, LSS for computing the activation gradient, LSS act, and their combined throughput, int4. We compare these to a typical 16-bit floating-point matrix multiplication, FP16, method provided by Cutlass. We perform this comparison using a NVIDIA RTX 3090 GPU, which has a maximum throughput of 142 FP16 teraflops and 568 int4 teraflops. We found that as the matrix size increases, the extra step of quantization becomes less of a burden. This allows our int4 operators to be as much as 2.2 times quicker than the FP16 matrix. Multiplication. Finally, we delve into the quantization overhead for each operator in the appendix section. Section Summary. The authors demonstrate the potential of their method to accelerate neural network training by evaluating their prototypical implementation, which is not fully optimized. They compare the throughput of their proposed HQM, LSS for computing weight gradient, LSS for computing activation gradient, and their average throughput with a baseline Tensor Core FP16 GEM implementation provided by Cutlass on an NVIDIA RTX 3090 GPU. As the matrix size grows, the overhead of quantization diminishes and their int4 operators can be up to 2.2 times faster compared with FP16M. Section. Training throughput. We're discussing the efficiency of our int4 training algorithm compared to the FP16 PyTorch AMP, specifically when training BERT and GPT-style language models. These tests were run on a system powered by 8 NVIDIA A100 GPUs. We adjusted several parameters such as the size of the hidden layer, the size of the fully connected intermediate layer, and the batch size. The results were visualized in a figure that showcases the enhanced speed of the int4 training. What we found was that our int4 training algorithm significantly improved the training speed. For BERT-style models, we observed a speed increase of up to 35.1%. Similarly, for GPT-style models, the speed increased by as much as 26.5%. If you're interested in the exact training times, they're detailed in the appendix of the paper. Section Summary. The authors compared the training throughput of the FP16 PyTorch AMP and their int4 training algorithm for training BERT and GPT-style language models on a system of 8 NVIDIA A100 GPUs. They found that their int4 training algorithm can achieve up to 35.1% speedup for BERT-style models and up to 26.5% speedup for GPT-style models, depending on the hidden layer size, intermediate fully connected layer size, and batch size. The training time can be found in the appendix.